Okay, so today what we're going to do is finish up our discussion about convolution, discrete time convolution. And last time we went through kind of what it was, how we compute it. And today we're going to talk about some of the different properties of discrete convolution and what their implications are for how we do system analysis and how we analyze discrete time systems. And then we're going to talk about a special operation that's unique to discrete time systems that we don't encounter in continuous time ones, and that's the process of zero padding and just how that affects convolution. Then we'll address the issue of how are we going to do convolution when we have periodic signals. The techniques we've developed, particularly the numeric ones, are really easy to use for finite length sequences. And we've seen how we can adapt them if we need to for infinite length sequences. But what about periodic signals? And we'll see a special way to work with that and how convolution plays out with periodic signals, which gives rise to a unique kind of convolution called circular convolution that only really occurs in discrete time systems, and we don't have that to deal with that in continuous time systems. So we'll see about what that's all about and how to compute those, and then come back and tie this up with looking at how we can use this strange new process called circular convolution to perform the normal kind of or linear convolution when we have signals that actually aren't periodic, but how we can still adapt it to get convolution results when we're after linear convolution. So that's what's ahead. There's our convolution formula in discrete time systems. We've spent quite a bit of time parsing that and seeing what it implied in terms of operations. Today we want to look at it as a mathematical operation and talk about its various mathematical properties and what results that gives rise to for continuous time system analysis as we use convolution to determine what the output of a linear time invariant system is for a given input. Turns out the convolution process is a commutative process, and if you remember your early mathematics, that implies that the order of the operations and the operands doesn't matter. So if I convolve an x with h, I get the same answer as if I convolve h with x, meaning if we plug x and h into our convolution formula, one of the two has to be flipped and shifted relative to the other to perform this convolution operation. And the fact that it's commutative means we get to choose which one of these two, which are the two signals we're going to flip and shift around. So the commutativity, which means that the order doesn't matter, gives rise to this result that we get to choose which of our two signals that we're convolving together we're going to do the more complicated processes to. And typically we'll choose the less complicated signal to do that with. Convolution is also an associative operation, which, if you remember, associativity implies the way we do groupings of multiple operations doesn't matter. We get the same result. And so mathematically, we'd say if I was convolving a function f with another function g, took the result of that convolution and convolved it by a third function h, I'll get exactly the same answer as if I first convolved the g and h functions, took that result and convolved it with f. And so if I have multiple convolutions to carry out, which order I do that combination in doesn't matter as well. Now, this particular operation, even though it's really a mathematical statement, the associativity also gives rise to an implication in system analysis. Not only does groupings not matter, but if we interpreted this associativity statement using our linear time invariant system understanding of convolution, where x is an input signal, h is a impulse response or unit sample response, and if I had two different ones, it would say if I take a signal, x of n, and run it through a system that has a unit sample response, h1, take that answer and convolve it with another H2, I get the same answer as if I first convolved the two unit sample responses, took that answer, and then convolved my input signal with it. We could do that graphically. Let's say if we had a system, a linear time invariant system with a unit sample response H1, and I put in a signal X, then what comes out of that is we would call Y then, but that's just the convolution of X with H1. If I took that answer and ran it into another system with a unit sample response H2, so I have two different linear time invariant systems in cascade or in series. That's kind of describing what we have on the left side of this equation. We take an X, run it through a system H1, take that answer and run it through H2. We get the same answer, the same output signal, if we had taken X sub n and run it through an equivalent system, a single block of two H's, H1 and H2 in series, where the unit sample response of that combination, that series combination, can be found by convolving H1 with H2. And so we could create an effective unit sample response for the series combination of two other linear systems by convolving together their unit sample responses. And so that's the statement, the system statement that this associativity property is saying to us. So if I have a cascade set of systems or a series connected set of systems, their overall unit sample response is found by convolving the individual unit sample responses. And that holds if I have 2 or 3 or 4 of them. As long as they're all in series, we would convolve together their unit sample responses. Another property we look at for mathematical operations like convolution is it distributive over some other mathematical operation? And in this case, we'd be looking at, is convolution as an operation distributive over addition? And it is. And that statement of being distributive over addition is, as we write it out as a mathematical statement, actually ends up describing the key property of linearity, which is superposition. So here's how we would mathematically demonstrate that convolution was a distributive had the distributive property over addition. It would say if I took two functions and added them together and then did my convolution with another function, that I should get the same result as convolving h with one of the functions and adding that to h convolve with the second function. Now, if we just looked at this statement mathematically, and if we knew nothing at all about convolution and we interpreted this as being multiplications, you would recognize that yes, this is a true statement mathematically, because multiplication is distributive over addition. Well, so is convolution. When we recognize this as a convolution operator, it works the same way. Now, in terms of linear time invariant systems, we could say this is describing, this term here would be if I take an input signal x1 and run it through a system that has a unit sample response h of n. What comes out we'll call y1 of n. So here's our y1 of n. And if I take a second input, call it x2, run it through that same system to produce another output, y2 of n, then if I make a third input signal made up of the sum of the first two, x1 plus x2, run that through the system, I should get the same answer. That answer should look like the sum of the original answers, y1 and y2. And so this again is just restating the superposition property of linear time invariant systems this way because of additivity. It also has another systems interpretation, and that is telling us how we can deal with systems that are combined in parallel as opposed to series. Here, if I have two parallel connected series, or two parallel connected systems whose outputs are then joined together by a summer, to produce the final output, and we present the same input to both, we can, using this property, define that the overall effective unit sample response of this parallel combination of H1 and H2 is in fact the sum of their individual unit sample responses. So if we look at this output term y of n, it's the convolution of x of n with h1 of n. Well, that's what's coming out this leg here. And when we convolve x of n with h2 of n, that's what's coming out here. When we combine those together, we create our y of n. And if convolution is a distributive function, or distributive operation, then this side has to be equivalent, and that would be the input signal applied to some other single system whose unit sample response is the sum of the original ones, H1 plus H2. And so we have rules now for how we can combine systems that are both in cascade or in series and in parallel. This is equivalent to a single system that I just simply add their unit sample responses together, and I'll get the same output provided this system as I would to this more complicated parallel combination. So if we're presented with a complicated block diagram of a number of interconnected systems, we could use these properties to determine what is an overall unit sample response for the combined system by putting together properly the series and parallel combinations of them, very much like how you would combine impedances in series and parallel to come up with an equivalent impedance. Now, convolution also has the property, because it describes for us a time invariant system, it also has to operate certain ways with time delays in our signals. Namely, if we create an output by convolving an input signal with a unit sample response, or simply mathematically say if we convolve two different functions to create a third, if I put a small shift in one of those functions, I should get the same output, the same result from the convolution, except it should be delayed by the same amount of time I delayed one of those input signals. And that's simply, from a system standpoint, a restatement of shift invariance. If y of n is the convolution result of x of n and h of n, if I delay the input signal by capital N1 samples, I'll delay the output by the same number of samples because we have a shift invariant system. We could extend that to either of the two signals that we're convolving. If I apply a delay N1 to X and a delay N2 to H, then again, the convolution result of those two signals will still have the same shape, look like y of n, but now it will be delayed by the sum of the individual time shifts from X and H. And now we come to a very important property of convolution, and that's what happens when I convolve anything with a unit sample sequence or a delayed unit sample sequence. And this mirrors the convolution with impulses properties that we had in continuous time systems. Namely, if I convolve anything with an unshifted unit sample, I get that original function back without any change in scaling, in amplitude, or position. Just get it back directly. If I convolve a signal, though, with a delayed version of a unit sample sequence, I get back that original signal, but it will be delayed by the same amount as the delta sub n was delayed. So if I delay delta sub n by n1 samples, I'm going to shift my signal over by n-1 samples as a result of convolving those together. This then tells us how we could describe the unit sample response for this delay block we've been talking about in our block diagrams of digital filters. So we said the job of this block was to take x sub n in and produce x sub n minus 1 out, or x sub n minus however many delays we have in here. Well, if this is true, if we put in x sub n and get out a delayed version of it, this must be the unit sample response for our delay block. And so if I have a block that delays x by 1 sample, it's the h of n, the unit sample response for this delay block must be delta of n minus 1. Now notice when we say we're going to shift x by n1, what that means is whatever was at index position n equals 0 in x sub n will now be positioned at n1, capital N1, after we do this convolution. So it's shifting the 0 point, the reference point, over to be now at position n1. And as a result, moving all the sample values the same amount. There's a number of other minor properties of the convolution process. One that might bear mentioning is that if I convolve two causal signals, the convolution result will also be causal. There's a number of others that you can see in the textbook and the reading. Less important, have less impact on how we analyze linear time-invariant systems. So let's move on to an operation that we're going to look at. How does this operation affect a convolution result? And this is going to seem like a strange operation. We're going to look at zero padding. What is zero padding? Well, zero padding, exactly as the name implies, is padding on some zeros, appending on some zeros to the end or the beginning of a sequence that we have. So it's appending extra zeros to the beginning or end of a sequence before we do a convolution operation with it. So if this was an input signal x sub n and it was a finite length signal, had the values 1, 2, 3, 4, 5, 4, and then zeros everywhere else. A zero padded version of that signal would be 1, 2, 3, 4, 5, 4, and some number of zeros afterwards. Now, x sub n, we understand that x sub n has the value of 0 beyond this point anyway. What we're doing by including the zeros in here is saying, I'm going to actually explicitly include those extra zeros in my convolution process. So it appears like it makes the sequence length longer, although it hasn't changed the non-zero value length of the signal. We'd still say this has 1, 2, 3, 4, 5, 6 non-zero samples. But when I'm counting positions for how many columns I need in a sum by column convolution, I'm going to count these as well. Turns out we can append zeros to the beginning or the end. They would both be considered versions of zero padding. And we want to investigate, if I do this to a signal, does that affect the results of convolution when I use that signal with the zero padding? So we want to explore what effect does appending extra zeros to the beginning or the end of the sequence have on a convolution result? Does it alter the length of the result? Does it alter the starting index of the result? And most importantly, does it change the actual numeric values that we get out of the convolution process? We don't want it to, but let's explore whether it's going to be a problem or not. And probably easiest to explore this by way of example. So this complicated slide is just running two different signals through our sum by column table. So as it's defined here, x sub n is a non-causal signal that has 4 sample values, 1, 2, 3, 4, where n equals 0 is at sample value 2. My second function, we'll call it h of n, has 3 samples, 5, 6, 7, where the 7 we define as the n equals 0 term. So we would say if I'm going to do a sum by column convolution of these two, I need 1, 2, 3, 4, 5, 6, 7, minus 1. I need 6 columns to do that with. 1, 2, 3, 4, 5, 6. And the starting index of my result is going to be, well, let's see. Our first value here is at index minus 1. Our first value here is at index minus 2. So the first index coming out of my table is going to be minus 3. And if we put our x of n down the side here, our h of n across the top, we have 5, 6, 7, then 2 times 5, 6, 7, then 3 times 5, 6, 7, then 4 times 5, 6, 7. Add them all up, and we get this for our convolution result. The values 5, 16, 34, 52, 45, and 28. Now we want to see what would happen if let me throw in some extra zeros now. Let me put an extra 0 in front of my 4 samples of x sub n, and maybe 1 after it. And do the same for h of n. Put an extra 1 in front and maybe 2 extra ones in back. And let me count those in my counting of how many columns I need. So if I included these extra zeros in my convolution, so now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers to convolve. So I need 11 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we'll just keep these just as they're shown. We'll have x sub n being, as we see here, 0, 1, 2, 3, 4, and a 0. H of n will start with 0 as its leading coefficient, and 0, 5, 6, 7, and 2 zeros after that. So when we multiply our h by our first x sub 0, we get just all zeros. When we multiply it by our next x value, which is 1, we get our 0, 5, 6, 7, and so on. And we run that through our sum by column method, tally up all our columns. We see that, in fact, we get exactly the same numeric answers that we got previously, which is good news. For a starting index here, we would say I would add -2 to -3 and get -5. So our first value out of this column is at -5. And if we compare what we got here to what we had previously, we got exactly the same numeric values out as we did before, which is the most important thing. So appending those extra zeros didn't affect the numeric answer from convolution. What it did do was kind of shifted us over, although we're still, if we did our accounting of the starting index right, we still get the correct indices going with each of our terms. And if you notice back here, to our original values that we had, we got 2 extra zeros in front and 3 behind. Well, that exactly relates to what we inserted in x and h. We put 1 in each of those. They ended up in front of our answer. We put a total of 3 zeros after x and h. They showed up after our convolution result in the output. And so zero padding does not affect the numeric results of the convolution. It makes our answer look longer, even though the non-zero length is not changed. It will change the starting index of our answer, but it will do it appropriately so that the non-zero samples still end up with the correct indices. So basically, this all says that adding zeros at the beginning and the end, as long as we account for them, is a benign thing to do. It doesn't affect the convolution result in any negative way, other than giving us more computations to do. What we get is if we zero pad our inputs, we get a zero padded result, where the amount of padding is exactly the sum of whatever padding I did before and after my original 2 signals. So here again, where I padded 1 extra in front of each of x and h, I got 2 extra ones in front of my y. And when I padded 3 extra ones in total after x and h, I got 3 zeros extra after y. So some of this summation then is that zero padding doesn't hurt us if we do that in a convolution. It just gives us some extra computation to do. We get some extra long answers, but all those extra terms that get added will all be zeros. And if I know how I padded my input signals, I can predict how to remove the padding from the output of the convolution. So that's all good news. Zero padding doesn't affect the convolution result. Now, why we would ever want to do that? Well, we won't have a good answer for that until we get through a couple more things. First is looking at what happens if we do a convolution with one or two periodic signals. Now, because we have a linear time invariant system, it has the property that if I put a periodic signal into it, the signal that comes out has to be periodic as well and has to have the same period as the input signal. Or another way of saying that, it has to have the same fundamental frequency as the signal coming in. Now, don't be confused. This is talking about taking a discrete time signal and putting into it a periodic discrete time signal into a discrete time system, And what comes out then has to be a periodic discrete time signal. We looked previously at what happens by the sampling process, and if I have a periodic continuous signal, does that end up in the discrete domain as a periodic signal? That's a whole nother issue and question. Here we're working with a signal that's definitely periodic in the discrete domain, put it into a linear time invariant system, and what we're saying is it's a property of linear time invariant systems that you have to get a periodic signal out, and it has to have the same period. So since that's the way linear time invariant systems work, and since convolution describes how linear time invariant systems work, convolution has to also have the same property. Has to work so that if I convolve a periodic signal with some unit sample response of a system, the convolution result has to have the same period, has to be periodic. Well, let's do a couple of test cases and see that that's so. Here's a periodic signal. It's like a sawtooth wave. It goes 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and does that forever. And I'm going to convolve that with a finite impulse response system. So I have a system that has a unit sample response that has these three samples, 5, 6, 7, happens to be non-causal, happens to be, but that's fine. We're just doing convolution here. And if I convolve this sequence, this finite length sequence that has 3 non-zero samples with this periodically repeating one, run it through the convolution process, which means take this, flip it, and shift it by the other, that convolution result would look like this. We get a different shape function, but it is periodic, and it's periodic with a period of 1, 2, 3, 4. But every 4 samples, it repeats the same pattern, matching the periodicity of the input signal. If I used a different length unit sample response for the same signal, like how about if I put an n equals 4 sequence into something with a unit sample response that's 4 wide, still FIR, that convolution result would look like this. We still get 1, 2, 3, 4, 1, 2, 3, 4, a periodicity with a period of 4 samples. So different shape, but the length of the unit sample response didn't change the length of the periodicity. Now you might notice something was different over here. These didn't look like they're part of the periodicity. Well, these are the lead-in to our periodic result. These are due to the fact that I did this convolution not like this repeated, but like it started right here and then repeated forever. I didn't take account for repeats over on this side. And so when I start the convolution, we flip this H and was running back this way and not overlapping anything. And then as it shifted on, it slowly overlapped more and more and brought this rise up until we got to the place where H of n was completely overlapping with my X of n, in which case it just created this periodically repeating pattern. So you could think of this as this would have been, if this was my input and I turned on a periodic signal on my input and started it at this index n equals 0, Here's our transient response to it, kind of a natural response of this system, and then the steady state response, this repeating sinusoidal pattern. Okay, now so far the first two examples, we had the same input period or input frequency. I changed the length of the unit sample response. What if I do change the input signal's frequency? So now it's a repeat pattern of 5 length, 1, 2, 3, 4, 5, then 1, 2, 3, 4, 5, and convolve that back with my original h of n that had a length of 3. This time again, we get a periodic result with 1, 2, 3, 4, 5 samples in its repeat. So again, it changed the shape, but the periodicity and the period were preserved by convolution with this unit sample response. So yes, convolution does have this proper behavior with periodic signals that matches that of a linear time invariant system. It gets a little more complicated, though, if I have two periodic signals, because now how I do the convolution, how I set up my sum by column table gets a bit messier. If both the signals that I'm convolving happen to be periodic with the same period, the convolution result will be periodic with that same period, but the process that I need to use to compute the convolution result is what we call circular convolution, the convolution of two periodic functions that are going to overlap each other forever. We designate that with a little circle around our convolution symbol that usually signifies this special circular convolution. Now, what do we mean by circular convolution? The kind of convolution we're used to is what we would technically call linear convolution. We have two functions, we're going to flip one and shift it past the other, and at each position we'll multiply all the samples together, add them all up, and get a new value, and shift it over and just keep repeating that process. When I have periodic functions, two periodic functions that I'm convolving, I have this situation where there is always overlap, and as one part of my signal shifts by the other, the rest, a new part of the next periods comes in place. And so I have a repeating pattern and always have perfect overlap with my two functions. We have a shorthand way to compute those rather than filling up a large sum by column table or doing flip and shift with these periodic signals. We have a way to visualize and do that computation in a special way to carry out this implied operation of circular convolution. Let's take an example. Here's a periodic input signal. It has a period of 4. The samples go 1, 0, minus 1, 2, 1, 0, minus 1, 2. And let's take a unit sample response that has a 3-length periodicity, 1, 2, 3, excuse me, 4 length, 1, 2, 3, 4, 1, 2, 3, 4. They have to have the same period. And I want to know what happens if I convolve this function with this function, my x with my h, using a circular convolution because they're both periodic signals. Well, if you recall back the first week, we introduced briefly a circular display for a periodic signal, where I could take just one period of that signal, put it in a circular display, and that would represent the signal and its repeating values by just going round and round and round that circle. So we would draw a circle, we would divide it in however many subdivisions we needed for the number of samples in one period. In this case, I have 4 samples in a period, so I'll break up my circle into equal parts, into 4 equal parts. And we usually start over on the center right of the circular display, and that's where we put the sample value at n equals 0. And typically we'll go around the circle counterclockwise. So I'll put x1 here, x2 here, x3 here. You could do it either way, as long as you're consistent, either direction, as long as you're consistent. My h of n then would be similarly, we put our n equals 0 value over here and go around counterclockwise. So I would expect to see 1, 2, 3, and 1 on this one. And 1, 0, minus 1, 2 and for x. And those are the circular displays for those two signals that both have a period of 4. Now, by using this same kind of display, where we superimpose one inside of another, we can carry out our circular convolution process. Let's see how to do that. For convolution, we need to change the argument of our functions to k. Well, that's just substituting the variable. It doesn't change the numeric values at all. For one of the two functions, we get to choose which one we want to do it with. We're going to do it with x this time. Excuse me. I need to reverse it because of the minus k and then shift it by n. All right, well, as you might guess, reversing means I'm going to take my x of n and reverse it. So x of minus k has the same values, still starting here at n equals 0, but instead of going counterclockwise, I'll put them clockwise around. So we'll do x of 0 here, x of 1, x of 2, x of 3 will go this way. And we'll put our 1, 0, minus 1, 2 around that circle. And so we have the circular display for our original H signal. We have the reversed version of the display for our X signal. And now to do a convolution, we'll put one inside the other. And for every index n, we'll apply a different shift to our reversed one here, and then perform the convolution at each point around the circle. Let's see how that works. So for n equals 0, I need my h of k. All right, well, we know how that looks like. It's 1, 2, 3, 1. I need my x of minus k, so I need it reversed and not shifted. So we do the reversed version of x inside here, 1, 0, minus 1, 2, going clockwise around. I won't put any shift in it. I'll just leave it like this. And now I do the convolution by multiplying and adding each term together. I take 1 times 1, add it to 2 times 2, add it to minus 1 times 3, add it to 0 times 1. Multiply those together, add them up, and get a value of 2, which is the result of this circular convolution for n equals 0. Then for y of n equals 1, we do the same thing. We take our h values, which are never moving. It's always 1, 2, 3, 1. You take our x of minus k again, and now I have to rotate it by 1. So we take our x of minus k and rotate it counterclockwise 1 position, so that we have now 1, 0, minus 1, 2, still going reverse around, going clockwise around the circle, but now rotated 1 position. That's how we've applied the shift now, the minus k plus n. We've shifted it 1 place for n equals 1. Do all the products and sums again. 0 times 1 plus 1 times 2 plus 2 times 3 minus 1 times 1. And we get 7 for that output. Now my two functions have a period of 4, so I know my output also has a period of 4, so I need 2 more of these and then we're done. So let's do the n equals 2 version. We keep our h as it was. The x of minus k, we're going to shift now 2 positions. So it starts here, 1, 0, minus 1, 2, around the circle. And then again, we just do the products and sums. Minus 1 times 1, 0 times 2, 1 times 3, added to 2 times 1. add them all up and get 4. And then you see how it goes. We just have to do it one more time. For n equals 3, we'll take our x of minus k plus 3, now rotate it 3 positions around. So we have the 1 here, 0, minus 1, 2 around the horn. Do our products and sums. 1 times 2, added to minus 1 times 2, added to 3 times 0, added to 1 times 1, and get 1. And we're done. So when I convolved, did a circular convolution of 2 periodic signals with a period of 4, I got another signal with the same periodicity, the period of 4, and the answers were 2, 7, 4, 1, and that would just repeat 2, 7, 4, 1 infinitely in both directions. So that's circular convolution, and that's how we do convolution when we have 2 periodic signals that have the same period, producing a third periodic signal with the same period. Any questions on that? Does that make sense? See how the process runs? Okay. Well, now we're going to backtrack a little bit and see why we needed to talk about zero padding. There are instances where we want to do linear convolution, standard plain vanilla convolution of probably finite length sequences. And yet, all that we have available to us is the mechanics of circular convolution. That by the nature of the mathematics we're using, the operations we're doing, I can only do circular convolution. I can't, but what I want is linear convolution. And so I'd like to have a way to take the mechanics of circular convolution and jury rig it so that it gives me the linear convolution result. And that's what zero padding's for. Zero padding takes this kind of circular operation, inserts a bunch of zeros to spread out the copies, the periods, so that when we do the circular convolution, they don't overlap. The different periods don't overlap, and I effectively get linear convolution with a whole bunch of extra zeros on the end. Well, why would we ever want to do this? Well, it turns out, just like in continuous time systems, we don't really like doing convolution in the time domain. The computation is cumbersome. It's much more efficient if we do it with transforms, particularly Fourier transforms, and in this case, particularly discrete Fourier transforms, or FFTs, fast Fourier transforms. Those work really well on computers. So when we want to do convolutions, we'd rather transform them and do them over there in the transform domain and then bring them back to the time domain, just as we did in continuous time systems. And yes, we're going to learn how to do that all again in this course. But as a preview of what's coming, it turns out that one of the consequences of having a discrete Fourier transform is the only kind of convolution it's able to do is this circular kind. And so while I want it and need it to do linear convolution, it can't support that on its own. It doesn't do that naturally. It naturally does circular convolution. It's one of the downsides of the discrete Fourier transforms. Yet to be useful, I want it to do this. So we'd like a way to cheat the system a little bit, to turn circular convolution into linear convolution. That's what zero padding does. So sometimes we want to use the mechanics of circular convolution to perform linear convolution. How do we do that? Well, circular convolution is going to treat our 2 input signals as if they're periodic with the same period n, where n is however many positions we have around the circle of our circular convolution computation. If we're trying to perform a linear convolution of 2 non-periodic finite length signals, we can do that actually using a circular convolution mechanism. But what we need to do is to zero pad our 2 signals to the correct length so that the result is a linear convolution result, not a circular convolution result. And again, zero padding just literally means add some zeros to the end of each of them. Now, the really crucial question is, in order to make this work, how many zeros do I have to add? And the answer is actually pretty straightforward. To get a linear convolution result out of a circular convolution of two zero padded signals, I need to zero pad my two signals to the same length, and that length is determined by the length of the normal result of a linear convolution, meaning my original two finite length signals, x and h, before I zero pad them, I would add their individual lengths and subtract 1. That was the length I needed for a linear convolution result. Well, what we do is take x and h, add zeros to the end of each of them so they're both have the total convolution length, length of x plus length of h minus 1. So for example, if I had this signal, x of n was minus 1 and 2, only a 2 sample long finite length signal, and h had 3 samples, 1, 2, 3. Doing a normal linear convolution using our sum by column method, we would say, okay, well, the starting index here for x is 0, the starting index for h, so the starting index for our result is 0. The length of the result, though, and this is the critical thing, we have 2 samples in x, we have 3 samples in h, so 2 plus 3 minus 1 is 4. I need 4 columns. I'll get 4 non-zero sample values out of the convolution result. And then if we just churn through the sum by column, we put our 1, 2, 3 sample values of h across the top, put our minus 1 and 2 sample values of x of n down the side, do the convolution results, take minus 1 times h of n, take 2 times h of n and shift it over, add up our columns, and we get the linear convolution result of these two short signals is minus 1, 0, 1, and 6, starting at n equals 0. Let's see if we can get that same answer out of a circular convolution. So I'm going to zero pad x and h, and then perform a circular convolution with the zero padded versions. The length we need for the zero padding is again the same as the linear convolution result length, which is take the number of samples that aren't 0 in x, add it to the non-zero length of h. In this case, 2 plus 3 minus 1 still gives us 4. And I want x of n to be 4 samples long and h of n to be 4 samples long, and I'll make them that way by appending zeros. I'll add 2 zeros to the x, I'll add 1 zero to h, so they're both now length 4. After that, let's put those through a circular convolution. So we take our h and put our 1, 2, 3, 0 around the outside. Our x will reverse x and do minus 1, 2, 0, 0 around the outside there. And then let's run this through a circular convolution. For y of 0, we set up our h, 1, 2, 3, 0. Take our x, minus 1, 2, 0. Don't shift it. Do the products and the sums and get minus 1. For y of n equals 1, EH stays the same. 1, 2, 3, 0 around the outside. We shift the x by 1 position so that now it's minus 1, 2, 0, 0. Do the products and the sums, and we get 0. Take x, n equals 2. Take our x that's reversed, shifted 2 places now. So it's minus 1, 2, 0, 0 around that way. Do the products and sums and get 1. And then finally do that for n equals 3. Moving the x3 around 3 positions, doing the products and sums, and getting 6. And so using circular convolution with zero padding, we get minus 1, 0, 1, and 6. Doing the linear convolution using sum by column, we got the same answers. And so I've been able to use the mechanism of circular convolution to perform linear convolution. Now, we won't do this way. We'll want to do this effectively using transforms, but this is the good news. This gives us a clue to how we'll be able to adapt using transforms to do linear convolution when all we have available is circular convolution. That's the end of our unit on convolution. We've now wrapped up everything that we need for this. This is the dividing point, the end of all the material for the first midterm exam. And so please check the Canvas for the learning objectives for that exam. That'll be coming up next week. Please work on homework number 4. You're now ready to attack all those problems.